treating industrial comminution as a black box can be lethal. From dust explosions to system breaches, neglecting the chaotic reality of particle behavior leads to catastrophic failure. Modern AI changes this by using acoustic sensors and predictive models to anticipate hazards before they reach a critical mass. In modern precision manufacturing, such as pulverizing silicon graphite for EV batteries, the margins are razor-thin. Thermal and fluid dynamic fluctuations can ruin million-dollar batches. AI-driven controllers now dynamically adjust pressure and flow to maintain consistency and prevent failure. Comminution methods vary, from the brute force of ball mills to the precise fluid dynamics of jet mills. While ball mills face issues like contamination, jet mills rely on supersonic collisions. AI now bridges the gap by using acoustic analysis to predict and prevent blockages. Industry 4.0 is moving beyond guesswork. By measuring energy consumption and mapping it against historical data, AI optimizes operations to target specific energy consumption levels, moving past the limitations of traditional, poorly tuned systems. Mathematical models for machinery often look perfect on paper, but reality introduces issues like hopper rat-holing or electrostatic blinding. Live PLC-linked AI monitors these systems, detecting deviations from the ideal and intervening instantly. Geometry is destiny in high-speed systems. Expanding air can cause significant temperature drops, leading to thermal shock and structural failure. Generative AI helps optimize housing designs to survive these cyclic loads while reducing weight. Elegant equations like Navier-Stokes often fail to capture microscopic reality, such as irregular particle shapes. Physics-informed neural networks, or PINs, are now used to solve these equations while automatically correcting for complex boundary conditions. Traditional simulations can take weeks. AI surrogate models bypass this bottleneck by learning the physics manifold from thousands of simulations, allowing for rapid predictions of particle size and wall erosion in mere seconds. A cyber-physical clone keeps a machine running smoothly by ingesting sensor data and filtering out noise. By watching the system break in the cloud, we can address potential issues before they cause real-world damage. Legacy control systems can be reactive and prone to overcorrection. Reinforcement learning offers a predictive strategy that balances variables to maintain precise output while enforcing safety limits, preventing system faults before they occur. Successful design must account for the shop floor reality, like microscopic surface defects that disrupt supersonic flow. AI computer vision inspects these components and compensates for physical imperfections by adjusting downstream control parameters. When models fail, physical redundancy provides a failsafe. In cases of thermal runaway, AI can trigger extreme measures like liquid nitrogen injection to shatter buildup, demonstrating that we can manage entropy even when the math fails. Instead of just designing a machine, we can design the constraints. Topology optimization removes unnecessary material to guide fluid flow perfectly, leading to significantly higher efficiency and lower energy consumption. Looking ahead, planetary scale processing will require new approaches. In zero-gravity environments, AI-managed flow control and autonomous drone swarms will be essential to handle materials and perform maintenance in an otherwise lethal setting. We cannot defeat entropy, but we can manage it. By combining first principles physics with AI, we have created systems that learn, adapt, and fail safely, turning chaotic processes into efficient, information-driven networks.